All right, my BC kids, here comes section 7.6 on arc length. There's times when you need to find the length of a graph on an interval. So in order to do that, you need to estimate the length of the curve. You divide it into sub-intervals, and then use the distance formula, actually, to find the lengths of each chord or each segment, and then add them up. So we need to remember the distance formula. Distance equals big old square root. We probably haven't seen this since, I don't know, maybe geometry. It is y2 minus y1 quantity squared, x2 minus x1 quantity squared, big old square root. Now it doesn't matter the order that you put these in. You could do the x2 minus x1s first and the y2 minus y1 second, because addition is commutative. You can change them around. So however you remember the formula, that's the deal. So in order to figure that out, you need 2 points. You need one point that is point number 1, that's going to be your x1, y1. And point number 2 is going to be your x2, y2. And so you can see the coordinates that you've got going on here. Now, if I want to estimate what this curve is, it's not so easy with the straight up distance formula to go between 0 and 3 because it's curved, right? So it's not a straight line. So the distance formula just using 0 and 3 is not going to work for us. So you've got to divide it into smaller sections to be able to figure that out. So they want us to approximate the length of the curve. Here's the function on the interval from 0 to 3, where the change in x is 0.5. So every 0.5, we've got a stoppage. That's where our coordinates are going to be. And so what we want to do is fill out the table. So the first one you want to find is the distance between 0 and 0.5. Then you want to find the distance between 0.5 and 1. Then you want to find the distance between 1 and 1.5. And then 1.5 to 2. And then 2 to 2.5, and then last is 2.5 to 3. And so I'll show you the first one, and then I'm going to set you free to try to fill in the rest of the chart. So if I just do this segment that goes between 0 and 0.5, I have 2 coordinates. I have this coordinate, 0, 4. I'm going to make this my x1, y1. And I have this coordinate, 0.5, 3.125. I'm going to make this my x2, y2. And then I'm going to fill in the distance formula. So I've got a big square root. Y2 is 3.125. Oh, I don't need a parenthesis yet. 3.125 y2 minus y1, which is 4, quantity squared, plus x2, 0.5, minus x1, which is 0, quantity squared. And so I subtract these first. I get negative 0.875 squared. And then I have 0.5 squared plus 0.5 squared. So I go to my handy dandy calculator and I figure out what that's going to be, and you get a lovely value that is 1.00778. I'm taking bunches of decimal points so that I can get a more exact answer. And so in my box here, in the length, my length is 1.00778. And I want you to take a minute, stop the video, and I want you to fill in the rest of these values. And then in the end, we're going to add them up and have a conversation. So stop the video just for a second. See if you can find those distances. Here's what you should get. Next one should be 8.80039. The next one is 0.625. The next one is 5.51539, which is actually the same as the next one down. And then I have 0.625 again. So if I want to know what the length of the curve is, I've divided it up into 6 little segments that when I add them up, I'm going to get an answer of how long this curve actually is. I get an answer that when I add them up, 4.08895. But is that really how long it is, or is that an estimate of how long it is? And how good is the estimate? So I know that because I am taking these little segments and adding them up, their lengths, it's really an estimate. It's kind of like the old Riemann sums. We were talking about that in class today. So if it's, remember how many rectangles you can fit under the curve? And what happens when there's more rectangles versus less rectangles? If there's less rectangles, then you end up with a less accurate answer. But the more rectangles you put in there, the more accurate your answer is. Same concept. I have 6 segments, but what if I divided it into 2 segments? What if I made it just 2 segments? That answer wouldn't be quite as accurate for the length of that curve. Or what if I put in 10 segments? Would that be better? Or what if I put in 100 segments? Would that be better? What if I put in an infinite number of segments? Would that be better? And you know the concept of what I'm trying to talk about. If you had an infinite number of segments that you divided this into, then that would create a more exact answer. Well, when you do that, that's like taking the integral. So the integral comes in because you're taking an infinite number of little segments, not just 6 in this case. This gave you a pretty good answer, but it's not a very exact answer. You can get even more exact by using an integral. So a couple things that have to happen in order for you to be able to do this for a length of an arc. One thing, think about it. This curve has to be continuous in the segment that you're looking, in the section that you're looking, in the interval that you're looking at. It has to be continuous. It can't be broken up, right? Because then you can't figure out what the length would be. So one thing is it's got to be smooth, right? The second thing is that it has to have a beginning and an end. You have to have a length. You're talking about the length of the arc. So it has to have a starting place and a stopping place in order for you to be able to figure it out, which kind of all makes sense. So we're mathematicians. We want to find the exact value of the curve. The process will lead us to making smaller intervals and taking the limit of the sums of the lengths of the line segments. You're hearing definite integral. Let's put a few restrictions in order to guarantee that the integral will exist. Suppose f is a smooth function in an interval from a to b. Find the arc length of the curve of the function over the interval. So the arc length on the interval, this is your the 2 points. This is like your x1, y1. This is like your x2, y2. They're endpoints. You got to have a beginning and an end. And it has to be smooth. The function is smooth on the interval if it has a derivative that is continuous through the interval. All right, so they're all the specifications of how it's going to work. Let me try to show you how they derive the formula. Okay, so here's where the formula comes from. You have some kind of a curve here, and that curve has to have a beginning and an end. So I'm going to just make a smooth curve. Here's my curve. All right, and now here's my A, and here's my B. I have a beginning, I have an end. That makes this coordinate here, if you think about it, A, f of A, like they refer to it, and this makes this coordinate B, f of B. x1, y1, x2, y2. Now, if I were to take this and look at, this is technically the distance formula, but it really comes from the Pythagorean theorem. If I were to take 2 points here, let me take these 2, and connect them with a right triangle type thing where the hypotenuse is the connection. Right triangle. This horizontal segment would be my change in x, my dx. This vertical segment would be my dy, my change in y. And we're talking about the length. We're going to make this dl. Talking about the length of that hypotenuse. Now think back to the Pythagorean theorem, right? If I think back to the Pythagorean theorem, I know that, in my case, dx squared plus dy squared has to equal dl squared, right? Pythagorean theorem. Remember, for us, we're looking at deriving the length formula. So if I took this and solved for dl, I'd have to square root both sides, which means that dl would equal the square root of dx squared plus dy squared. Now let's put it into the thought of how how many of these little rectangles or these little triangles can I make, right? I could make an infinite number of those I keep wanting to call them rectangles, triangles. I could make an infinite number, make them smaller and smaller. I made this one relatively large so you could actually see the notation. But if I'm looking at what the actual arc length is, arc length, they call it L, go figure, right? Finally, they use a letter that makes sense. They call it L, and that would be the integral, because I'm going to have an infinite number of triangles in there, and it's going to be the integral of that distance formula that we just came up with here. So it's the integral of dx squared plus dy squared. Looks like this. So I'm going to have an infinite number of triangles that I'm going to add up. Now here's what's a little bit weird. Now I'm going to play an algebra game with you to get to where the formula is. So what I want to do is factor out a dx. Let me show you what that's going to look like. L equals, I've got the integral. Now where's your integral going? Your integral is going from a to b. They're your bounds. And if I factor out a dx, now I'm going to show you what it is, and then I'll tell you why it is in a second here. It's going to be a 1 plus dy over dx squared with respect to x. Anytime probably should put this up here too. Anytime you take the integral, it's with respect to x there. Is this really the same? Is that a legal math move? Will the math police come and get me? Because if I got common denominators with this, this would be dx over dx, or actually dx squared over dx squared. This is your dy over dx squared. So it really is the same thing as this. It's just written a little differently, right? Got a little different thing going on here. And the reason why we did it this way is because what does dy over dx equal? What's that the same thing? Can I call that something else? That's your derivative. And so really the final equation for the length of an arc is the integral from a to b of a big old square root with 1 plus the derivative of the function squared with respect to x. Because dy over dx is the derivative. And there you go. You just derived the formula. Here it is. Proof of the pudding. That's what you wanted. Same thing goes, it works the same way if you had y values. Okay? So let's try it. Let me show you how it works. These are relatively easy because you've got a straightforward formula to use. That formula, I'll kind of keep it on your screen here. Here's the formula we're going to use. Same as this, whatever, typed or written. They give you this formula and they say, this function, and they say, find the length of the curve from 0 to 1. And you say, all right, not a problem. Well, job number 1 is you need to know what the derivative is. So you can put it in the formula. Well, the derivative, this one's kind of funky, right? I have a 4 square root of 2 over 3. Bring down the power 3/2. Take it to 1 less power. And the derivative of negative 1 is 0. All right, so let's see what we got. 3's cancel. Outside 4 cancels with the 2. And I end up with 2. I end up actually with the square root of, actually, no, right, 2. This is 2 here. 2 square root of 2, and then I have times the square root of x. Well, anything inside the square roots can combine. They actually can multiply, so I get 2 square roots of 2x. I'm going to leave that as a root form, and you'll see why in a minute for this one. Now I'm ready for the length formula. That's step number 2. Put it in the formula. Well, the integral goes from 0 to 1. Sorry, there's the puppy. 0 to 1. And I am going to put it in the formula. Here I go. 1 plus the derivative squared. 2 square roots of 2x quantity squared. With respect to x. All right, sorry about the dog. All right, so I'm going to square this out. I'm going to work my way through this whole hot mess and see where I go. I've got an integral still going from 0 to 1. I still have a square root. I'm going to see if I can square this and make it better. Because remember now I'm going to have to take the integral in a second here. So 1 plus. If I square the 2, I get a 4. If I square the square root, I get a 2x. Remember, the square root gets undone there. And so I'm going to clean it up so I can take the integral 0 to 1 of the square root of 1 plus 8x with respect to x. Well, nobody likes to do a square root, so we're going to make this really 1 plus 8x to the 1/2, and there I go. Now I'm ready to try to think about an integral for this guy. So I'm thinking of all the methods we've learned of how to figure out what an integral is, and so this one screams to me u sub, with my u being 1 plus 8x. My du is an 8 dx, which means that I have 1/8 du is my dx. And now I'm going u subbing. Oh, by the way, what else do I need to do? I need to get the new bounds. Might as well do that while I'm at it. U equals, my upper bound is a 1. 1 plus 8 times 1 gives me a 9. Lower bound is a 0. 1 plus 8 times 0 gives me a 1. All right, here it is. Now it's the integral from 1 to 9 of a u to the 1/2. My du has to be a 1/8, so I'll put that on the front. And this is my du. There's my u sub. All right, now I am ready to take the actual integral. U to the 1/2, add a power on, divide by that power, so it's u to the 3/2 with the 2/3 in front, going from 1 to 9. Can I make that any better? Yeah, this becomes a 1/12. 2 and 8 cancel. 1/4 times the 3 gives me 1/12. And I am u to the 3/2 going between 1 and 9. I'm running out of space. Good thing it's almost over. I've got 1/12. If I put a 9 in here to the 3/2 minus a 1 to the 3/2, that should get me my answer in the end. 1/12 times the square root of 9 is 3. 3 cubed is 27. 1, the square root of 1 is 1. Cubed is 1. 27 minus 1 is 26 twelfths. Oh, can I squeeze it in? They both divide by 2. 13/6. And that is my final answer for example number 1. Okie doke, let's try another one. Example number 2. We're going to go to the calculator for this one. Some of them will use calcs and some of them we'll do flat out. So example 2, find the length of the curve from 0 to 3. Okay, fine. So deal number 1, you got to find the derivative. All right, well this derivative is going to be your chain rule, right? You've got this quantity with a power, so you've got the 2/3 that's in front. The 3/2 comes down in front. Ooh, happy dance. They all cancel. Hold on a minute, though. Don't get too excited. Take 1 less power, 1/2 power. But times, don't forget chain rule, the derivative of what's inside. All right, bang, 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 bang. Ain't nobody in front no more. I've got a 2x, and I've got a square root of x squared plus 1. Again, I'm putting it as a root because when you put it in there and you know you're ultimately going to have to square it, it just is easier to see how to square it. So for this one, if you've got square roots involved, most times you probably want to do that. Here goes my length formula. The integral from 0 to 3. And I have a big old square root. 1 plus, the derivative is 2x square root of x squared plus 1 squared with respect to x. See if we can clean it up before we put it in the calculator, right? This is going to kind of be messy to put in a calculator with a square root of a square root. So, I mean, you can, if you want to, stop right there and put it in, but we're going to make it just a little bit prettier. I have a 1 plus. Square the 2x, 4x squared. Square the square root, x squared plus 1. Undoes it, right? and that is with respect to x. Can I make that any better? I think I can. It's going to equal a integral from 0 to 3, big old square root, 1 plus 4x squared times x squared is 4x to the 4th, and 4x squared times 1 is 4x squared. Well, that's way better to toss in your calc. So probably the way that I would do this is put it in your y1. Let me see if I can make a note over here. Put in your y1, 1 plus 4x to the 4th plus 4x squared, and make that to the 1/2 power, to the 0.5 power. If you do that and then graph it, and then for our calculators, if you go to F5, that math menu, and down to, I think it's number 7, it gives you the integral. And so you're going to put, it'll ask you what the lower bound is, what the upper bound is. Our bounds are 0 and 3. And then have it calculated out for you. And it's sweeter than sweet. It gives you an answer of 21. So you can pause and try that, but that's the deal. All right, example 3. Find the length of this curve. 2/3 x to the 2/3 from 1 to 8. Round your answer to the nearest thousandth. We can use a calculator. So again, all starts with the derivative. What's the derivative? So I've got a 2/3 constant. Bring the power down, it's 2/3. No happy dance, nothing cancels. 1 less power is x to the negative 1/3. And that's pretty much it. So let's see what that becomes. I have a 4/9 x to the negative 1/3. See how this one's a cube root now, 1/3 power, and it would be in the denominator. I'm not going to put this one into the form of a square root, or in this case a cube root, because when I go to square it, it's not going to do me any good. Where when it's a square root, it does you a lot of good when you go to square it, right? Because they undo each other. This isn't going to get undone. He's going to be a hot mess. So I am leaving him as an exponent this time. Now, if you were to change it into a root, that's fine, but it's easier algebraically to calculate this the rest of the way as being a fractional root, a fractional exponent there. All right, so let's see. We got our derivative. Let's put it into the length formula. My interval is going from 1 to 8. Big old square root, 1 plus 4/9 x to the negative 1/3 squared with respect to x. All right, well, let's see if we can, before we put it in the calculator again, make it any better. I've got the integral going from 1 to 8. I have a big old square root. I have a 1 plus square the 4/9, 16/81. Holy moly, that's ugly. But what happens with your exponents? If you take a negative 1/3 exponent and you raise it to the second exponent, do you add the exponents? Do you multiply the exponents? What do you do with the exponents? And hopefully you're saying, you multiply them. So I get x to the negative 2/3 with respect to x. So you can see why I left it this way, because it doesn't actually get rid of the root like the other two did. All right, this is what you put in your calc. Take a minute, see what you get. Let's see if we match. 7.28937, or something in that hood. Here you go. Example 3. Example 4. This one's a little different than the others because look at this guy. He is now an x equals. Well, guess what? The formula works exactly the same way. But watch, make sure that your bounds are y values, right? Before they were all x values, now you're looking at y values, but you treat it the same way. You want to find the derivative first. So here I go. My derivative is x prime would be, this would be the same thing. Let me just write it a little differently. This would be like 1/6 y cubed. And this would be like plus a 1/2, and where's the y in the bottom? Y to the negative 1. Just for the purpose of being able to apply that power rule, it's better to think of it that way. So here it goes. I've got 1/6. 3 comes down in front, goes to 1 less power, y squared. Plus, I have a 1/2. The negative 1 comes down in front, goes to 1 less power. and then I clean it up. 3 over 6 is 1/2 y squared. This is a minus 1/2 y to the negative 2. And again, I'm going to leave it that way as a y to the negative 2 for this case. So let's put it into our length formula. Length formula works the same way. I'm going from 2 to 3. I have a big old square root. I have a 1 plus derivative 1/2 y squared minus 1/2 y to the negative 2. But this time it's O squared, by the way. This time it's with respect to y. Now, you're going to toss this in your calculator. We're not going to actually take this. This gets really algebraically crazy. But if you put it in your calculator, you can use x's in your calculator. You don't have to say it's y. You can put y's in if you want to. The calculator will understand it either way. So you're going to toss this all in your calculator. We'll see if we match. Drum roll. Should be 3.25. All right, we got 2 to go that we did in class so that we keep up with where you're at, keep you in the same place that class went to. The rest of these are the homework problems. Here's the homework problems. The first 2 are multiple choice. Go figure, right? Multiple choice. We don't get those very often. First one isn't so bad. The second one takes a little discussion, and we talked about it quite a bit in class. But identify the definite integral that represents the arc length for this curve, the ln of the square root of x over the interval from 1 to 3. All right, so first thing you check, they all got 1 to 3, so you're all good with those. So you can't eliminate anybody based off of that. If I go to this, you know it starts with the derivative, so I want to figure out the derivative of the ln of the square root of x. So that'd be the same thing as the ln of x to the 1/2 power. Well, ln's are 1 over whatever it is, 1/2, not 2. ln gives me 1 over x to the 1/2 power, but then I have to multiply that by the derivative of x to the 1/2. So 1/2 x to the negative 1/2. Well, what does that look like? If I put it all together, this would be like 1 over the square root of x times 1 over 2 square roots of x, right? The x would come down to the bottom and be a square root. The square root of x times the square root of x is just an x, so I get a 1 over 2x. That's a pretty cool derivative. So, which one of these would fit that for the arc length formula? It has to be, remember, if I put my length together, can I go over the left there? I'm going between 1 and 3. Big old square root. 1 plus the derivative, 1 over 2x squared with respect to x. So which guy fits that? Definitely not this guy, definitely not this guy, definitely not this guy. Gotta be B. B as in beautiful. The second one, number 2, this is what we're going to end with. Number 2, this one seems, you got to kind of work your way backwards out of it. The length of the curve is given by this integral from 1 to 5. If the curve contains the point 1, 4, which of the following could be the equation for this curve? Well, it all depends on this piece right here, because you know that that piece right there represents the derivative squared. All right, well, what was the derivative? If this is the derivative squared, 9x to the 4th, square root it, the derivative must have been 3x squared. But I'm trying to get to the curve. So if I'm trying to get to the curve and the derivative is 3x squared, really what I want to know is what's the integral? Going backwards, right? I'm trying to figure out what the function was. So if I'm the integral of a 3x squared, add a power on, divide by that power, gives me an x cubed. Well, I know that the original function had an x cubed, which means I can eliminate a. 1 over x cubed it is not. The rest of them all have x cubes, and I'm like, all right, well, let me go further here. So the next thing I know is that I have a coordinate that is 1, 4. That means my x, when my x is 1, my y is 4. So let's see who that works for. If my x is 1, will my y be 4? 3 times 1 is 3. 3 plus 1 is 4. Could be. This guy fits that. If my x is 1, is my y 4? This guy fits that too. Oh, more than one answer maybe? This one, if my x is 1, I get 7. So this guy, I can eliminate him. That doesn't work for the coordinate that I've got. So now I'm down to 2 equations. And I know that the derivative of the equation has a 3x squared in it. So let me go to B. What's the derivative of this term? The derivative would be a 27x squared. Well, that's not what my derivative is. So I can eliminate this guy. Let's try this one. This one, my derivative would be a negative 3x squared. But remember, you're squaring it. So the fact that it's negative, you don't care. It's going to square out of that anyway. It's going to turn positive. So your answer is C. And there you go. So that takes you through section 7.6, a relatively easy section because of the formula that you've got to be able to use to get it. So I will see you in class. Shoot me an email with any questions. Bye.